computer. Okay, so it's recording. Cool, and now I can share my screen. Share. Yep, desktop 2. So you should be able to see my slides. And yeah. So, okay. So can you see everything's fine? So, okay. Fine. So we are recording and you should see my slides. So, okay. So before we were talking about the detection of gamma rays. So in GV domain, so with pair conversion technique and at higher energies with Imaging Atmospheric Cherenkov Telescopes. So lectures by Natalia. And today I'm going to present you a complementary technique to the IACT, Imaging Atmospheric Cherenkov Telescopes. So which is using not sampling of the Cherenkov light on the ground, but the particles of the shower themselves. So let's get started. So as a reminder, so what we want to detect, we want to detect gamma rays in the TV energy range coming from distant sources. So when a gamma ray or there also background particles, cosmic rays, when they strike atmosphere, they induce cascades because the gamma ray is producing electron-positron pair in the vicinity of nucleus. So this is beta-Heitler pair production. For cosmic ray is a bit different. So a proton or an alpha particle or a firm nucleus is striking the atmospheric nucleus, and this is basically what they're doing at Large Hadron Collider. So they strike the particles, and this is governed by strong interaction. So, and there are cascades of secondary particles like charged pions mostly. So for cosmic ray, charged pions. So neutral pion is decaying into 2 gamma rays, and you have electromagnetic shower. And the pions that are charged, they like pi plus, pi minus, they're unstable particles. So they live 10 to minus 7 seconds or something. And this guy is living 10 to minus 14 because this is electromagnetic and this is governed by weak interaction. Okay, and there are lots of, let's say, shards. So, secondary particles. So gamma rays, muons, and muon neutrinos. And so you can see there are islands with electromagnetic showers. So it's a branchy structure. While for primary gamma ray, when a gamma ray is penetrating the Earth atmosphere, it's much more simple. So beta-Heitler pair production, and you got electron-positron pair. When the first interaction occurs at an altitude around 20 kilometers above the ground level. Okay, then these particles, they interact with the atmosphere via Bremsstrahlung. So this is when a charged particle is passing near in the field of in the Coulomb field of a nucleus. So due to the Coulomb interaction, the charged particles is changing its trajectory, and a photon is emitted, so a gamma ray. And these gamma rays, they interact with the nucleus, so they produce electron-positron pairs in the vicinity of the Coulomb nucleus, of the Coulomb field of a nucleus, and the approximate length of one generation, like gamma ray propagates until it produces pair, is around 1 kilometer, but it's varying. Well, it's a statistical process, so it's plus minus, and so yeah, you've got only leptons in this cascade. You don't have any hadrons, you have only leptonic particles. So all the processes are governed here by electromagnetic interaction. And here in the case of cosmic ray, you have electromagnetic, you have weak interactions. So, and particles are gaining higher transverse moment than in this case. So the extent in the xy plane, so if this is the axis xy, so in the plane of the Earth surface, you will have much more spread out shower. So yeah, this is just a reminder what are charged or particles like cosmic rays or gamma rays in neutral. So what gamma rays and cosmic rays are doing when they enter the atmosphere of the Earth. So they induce these cascades named air showers. And so if you have a 1 TeV gamma ray or cosmic ray, so it produces a shower, and the first interaction, okay, occurs at altitude of 20 kilometers. The peak where you have most of particles is around 10 kilometers, but then the shower, it fades out just because, well, particles are, when they break to more and more particles, each particle has obviously less energy. So it's a transfer, you see, so you have more and more particles, but each particle has less and less energy. So the at some point, particles, when they reach energy of about 70 MeV, 1 electron, so it's not able to interact via Bremsstrahlung because ionization losses take over. So these particles, they're merely, they're just not emitting. So they're ionizing the medium around, and no gamma rays are created. So you don't have cascade, the cascade is stopping developing. So it's fading. And the point where this happens is few kilometers above the ground level, typically. So the shower itself, it doesn't reach the ground really, but what reaches the ground is the Cherenkov light emitted by these particles. So charged particles that are traversing medium with a certain refraction index. So if the speed of particles is higher than the speed of light in the medium, they will be emitting Cherenkov radiation. And this radiation is, well, is directed towards the ground and creates a light pool of around 100 meters in radius. So IACT technique, the Cherenkov telescopes, they sample the Cherenkov light that is arriving on the ground level. And by the shape of the shower, they discriminate gamma rays from cosmic rays, so charged particles. And by the extent of the shower, you remember I was showing, so they can reconstruct the arrival direction. But for 100 TeV cosmic ray or gamma ray, so the more, you know, so the more is the energy. Okay, Douglas raised hand. So Douglas, can you ask a question, because I can't see chat, unfortunately.
I don't know. At this time, I'm at my place. I just wanted to know something, right? Let's say, you see, a cosmic ray hits our Earth surface. Will it like depends on the telescope position, like the concentration of the data that will be receiving? Will it depend on the position of the telescope?
Okay.
Or what will happen? Because if we were to put the telescope near where the radiation will start occurring, and then not near where the radiation is occurring, how will there be like some variance, or what? Will there be some sort of a variance?
You mean the relative position of a telescope with respect to the axis of a shower? I mean, the telescope is not exactly in the center, but aside, right?
Mm.
Yeah, sure. So it will be, the shower will be having, so you see the Cherenkov light has a very anisotropic pattern. So the extent is around 1 degree only. So if you're outside of this 1 degree cone, then you see much fewer Cherenkov photons. So then you will see first fainter events, and then you will see a different shape as it will be projected. So you will be seeing, well, the event will be, the shape will be like the elongation of this ellipse, it will be different. So by these, by the shape and by the light content, you can actually more or less, well, you can find out what's the impact parameter. or what's the angle between the axis of the shower, and that's what you're more interested in. So where is the source? So you want to know from where exactly the gamma ray or cosmic ray came. Is it from the source or is it from somewhere aside? Because you want to reject all the noise. So it will be impacting the image of the shower in Cherenkov light. So does it answer the question?
Yes,
Okay.
indeed.
Yeah, sorry, because in my version of Zoom, I don't know what's happening, but when I'm sharing screen, I cannot access the chat. So if someone has any question, just raise your hand, because I will be able to see that. So, okay, we can carry on. So yeah, so this is for the Cherenkov light, so detection of Cherenkov light. And for 100 TeV cosmic ray, so the more is the energy of the primary particle, the more Cherenkov emission will be created. And okay, the cascade, you see, so the higher is the energy, the deeper will be cascade going into the Earth in the Earth atmosphere. So it will be closer to the ground level, because this 70 MeV threshold, when the cascade starts to die out, so it will be reached at much lower altitudes. So the shower is more extended towards the Earth. So for 100 TeV cosmic ray or gamma ray shower, much more particles will be reaching the ground level. So the technique that I'm talking about today is to directly measure the particles which are falling on the ground, so from the cascade. And by detecting these particles, so we can reconstruct the properties of the primary particle, like arrival direction and energy. So as you can already see from this sketch, so this technique has already a major drawback, because you can only start seeing showers on the ground. Oh, sorry. You can only start seeing showers on the ground from much higher energies than for Imaging Atmospheric Cherenkov Telescope. So, so how do we actually detect that on the ground? So to detect very high energy gamma rays that have quite high energy and from showers of which can reach the ground, so we directly measure these particles of the air shower on the ground by specific detectors. So typically it's a metal tank, so filled with water. So an array of water tanks is placed over a Earth surface, and particles which are traversing the water tank. So they, as they move high energy particles from the air shower, as they are much more faster than the speed of light in water. So what is the speed of light? So the speed of light in water is around 0.77 of speed of light in vacuum. So particles are much faster than that, and so they emit Cherenkov emission while moving through the water. And the tanks are equipped with photomultipliers which sample the light. And like this, we can know that there was a particle traversing the tank. And as there are many tanks, we can reconstruct the whole development of the shower. So obviously you want to put these water tanks high up in the mountains at high altitudes, because, well, you can see clearly is that the higher you put them, the more shower particles you get, and the lower your threshold. So if you put your water Cherenkov arrays up here, yeah, you will be able to detect much lower energy gamma rays. So the example, so okay, why do we want to use water? What's so special about why not air? Why not empty tanks, or why not another substance? So yes, Douglas.
I just wanted to know, like, I don't only, like, let's say, can you give us like particular particles which we normally detect whenever we are using that type of way, like that type of an experiment? Is there like a constant particles that we usually detect? Like for example, I remember Natalia mentioned the fact that like you know the telescope which is in China, the one that usually detects neutrinos.
Yeah.
Like she mentioned the fact that we use water to detect neutrinos because when neutrinos are passing by matter, usually they don't interact with it, but we can slightly slow it down because it will be moving from ground and then to the water, and then that's how they usually detect it. So I wanted to know, like, if you are using this type of way, is there like a specific particle which we are constantly detecting it whenever we are using this type of telescope?
Okay, yeah, for neutrino is a very different story because neutrinos are not charged, so neutrinos are neutral particles, and neutrinos are only interacting via weak interaction. So the process, so they don't emit Cherenkov light. You see, only charged particles are emitting Cherenkov light, and neutrinos are not able to emit Cherenkov light. So it's a very different. So the detection technique is very different for neutrinos. So yes, indeed, there are water tanks with photomultipliers, but it's not via detection of Cherenkov light, but it's light flashes. So it's well, I don't particularly remember which light exactly. Is it scintillator arrays, I think? So, but here, so the idea is that, yeah, it is a charged particles. So it's moving through a medium, water, and as it's moving faster than speed of light, okay, so it's emitting Cherenkov light. And so this Cherenkov light emitted along the path while the particle moving in the water. So it is seen by photomultipliers, and photomultipliers sample this Cherenkov light. So that's the crucial difference. So that so when we're measuring air shower particles, so these are all charged particles, you see. So particularly for gamma rays, so electrons, positrons.
Okay.
So in the case of neutrino, it's different because neutrino, I think there is a chance of interaction with matter, so it's inducing launching a particular reaction, and these products of this reaction, the light is emitted, so scintillator arrays are sampling this light. So this is the idea. So it's not Cherenkov emission, or maybe, yeah, or maybe neutrinos set off a reaction in which charged particles are created which emit Cherenkov light. In any case, yeah, so it's not directly neutrinos. The neutrinos cannot emit Cherenkov light. So it's more like secondary products which are emitting light, and this is how it's detected. And for neutrino, okay, there is a very small chance that it will interact with the medium, while for the shower particles, so it's almost 100% chance that it will induce a Cherenkov light flash, which will be seen. So in this way, well, we can detect almost every gamma ray incoming with sufficient energy. Okay, I hope these replies and emphasizes the difference in the detection technique. So yeah, why do we use water? What's so special about water? So let's say water has much higher refraction index than in air. So in air, you have refraction index of 1.000 something. I don't remember, but it's close to unity. While for water, it is, well, at the speed of light is 0.077. So 0.77, and it's the reverse of that. So inverse of that, so it will be 1.3 or something, okay? And so the Cherenkov emissivity, so how many Cherenkov photons will be emitted along a unit of distance, like along 1 meter, for instance, and over the interval of wavelengths. It is given by Frank-Tam formula. So this is the expression. So this is fine structure constant, 1/137. So lambda is the wavelength. So it's UV domain, I don't know, 300 nanometers. And so V is the speed of particle. So it's close to the speed of light in the vacuum, but slightly less. And n, depending on lambda, this is the refraction index, which depends on the wavelength, because you have dispersion in the medium. So, but if you assume the same, let's say 10 TeV particle, so 10 TeV electron passing through air, so it will emit along 1 meter of distance. So yeah, 10 TeV electron, which was just created over 1 meter of distance, this electron emits around 20, or let's say 10, 15, 20 Cherenkov photons. While when this 10 TeV electron is reaching, or when it's passing through water, so because of the much higher refraction index, you will have 700 times higher emissivity. So one electron in water will emit already like 15,000 of Cherenkov photons. So yeah, this is much better for, so the Cherenkov flashes will be much more well, bright. So you will be, it's more reliable detection. And so also water is transparent for Cherenkov radiation, more or less. So you can see through water typically in the blue or UV domain. And okay, water is kind of quite common resource. I don't know, maybe in South Africa, not that much, but generally still water is quite available. So this is why it's most obvious choice for filling into these water tanks. So they're full of water. So an example of operating currently instrument which is using this technique is HAWC. So HAWC is the acronym for High Altitude Water Cherenkov Gamma Ray Observatory. So HAWC, so HAWC. So it's a collaboration of US, Mexican institutions, which is, so the array is located in Mexico, high up in the mountains. So it's composed of an array of around 300 water tanks. So yeah, so we can, I guess, have a look where is HAWC on the map. Yeah. So yeah, this is Mexico, and so it's located high in the mountains. So you see Mexico City, Puebla, and so it's located here in the national park. So Parque Nacional Pico de Orizaba, so in Puebla region. And yeah, here it is, view on the Google Maps. So 300 water tanks high up in the mountains, and it's, by the way, not far from the Large Millimeter Telescope. So they're neighbors. So yeah, now you know the location of HAWC. Yeah, so we can return to slides. So cool, yeah. So this is an array of 300 water tanks, which are used to detect air shower particles. So one water tank is not that small, actually 7.3 meters wide, and more or less 5 meters high, and each tank contains around 188,000 liters of water. That's a lot, right? And each tank is equipped by 4 photomultiplier tubes inside, so which are monitoring the water, and if there is a particle passing, so it triggers, so the Cherenkov light is emitted, and these photomultipliers, they are sampling the light. So yeah, located in Mexico, I already said. So altitude is quite high, so it's 4,100 meters. So it allows you to measure more particles, so have more reliable statistics and lower your energy threshold. And so HAWC was deployed and is operational since 2015 spring, and it more or less, it's sensitive to gamma rays with energies. Okay, 100 GeV, maybe it's very optimistic, but few hundred GeV, up to 50 TeV or even 100 TeV, depending on the well, because for most of the sources, their flux is rapidly decreasing with energy. So if you're lucky to catch a gamma ray with higher energies, okay, why not? So, and its very important virtue is that it has very wide field of view, which is around 2 steradians. So imagine, more or less, if you have 45 degrees 45 degrees angle of field of view. So that's this really a lot, especially compared to IACTs, which have maybe around only 5 degrees. So good. So here, you remember in the case of IACTs, we had to do gamma hadron separation. So the air showers, so there are two types of air showers, yeah, induced by gamma ray. But hadronic events, so the flux of cosmic rays is such that it's many more orders of magnitude higher than for gamma ray events from any type of source. So I guess 5 or 6 orders of magnitude. And so we need to discriminate because we want to filter out the background noise, which is represented by cosmic ray events, from the signal from the source, which is much more weak. So in the case of IACT, Cherenkov telescopes, so we were doing this separation on the basis of the image, so Cherenkov image. So particles of the shower, they emit Cherenkov light, right? And the showers in Cherenkov light, they looked quite different. So for gamma ray shower, it was more like an ellipse, elongated, like an elongated ellipse. And for hadronic shower, it was a big blob with many islands. So it was more like scattered because of electromagnetic islands. So there were several branches where electromagnetic showers were developing. And again, due to higher transverse momenta, so you have more extended kind of shower. So it's much more scattered. So the idea is we're very similar for HAWC. They don't see Cherenkov light, but they're directly sampling, let's say, the bottom of the shower, more or less. So you can see, okay, there is a very different structure. So they're using this kind of pattern of hits to discriminate. So the separation is done based on the spatial pattern of the hits observed by the detector when the air showers reach the ground. So what does it mean? So it means a different, if you look at the detector from the top, so and particles falling on the detector, so it will be a very different picture of how particles are striking the detector, the tanks. So for gamma ray showers, the bulk of the signal will be concentrated near the axis. So you have seen it here, right? And for hadron showers, so it will be more scattered and more broken apart. So this picture here, it represents what I just said. So on the left, you see a cosmic ray, so proton with energy of 24 TeV. So that is a simulations. So it, yeah, so it hits, you see, it's more, so yeah, this is the shower, and so it develops, so you have higher transverse momenta and electromagnetic subshowers. So in the net result is that it strikes, you see the detectors, which are the water tanks which receive signal. So the picture is that these detectors which were triggered, so the pattern, it's much more scattered. So the signal is occurring in many distant water tanks. So it's a scattered pattern, while for gamma ray, most of the shower particles will be more or less falling on in a concentrated circle around the core. So the only, you see only, well, the detectors which will be triggered will be in a narrow, much narrower area than in the case of hadron. So this difference in the spatial pattern of interaction on the ground is used to discriminate. But I have to say that it is much more, let's say this background projection is less reliable than for Cherenkov image, because for Cherenkov image, the well, the Cherenkov light, so each particle, so here you sample only like a specific slice of the shower, right? Some particles which are contained in the shower, and not all of them, for instance, are reaching your detectors. But in the case of Cherenkov light, so all particles which were emitting Cherenkov light will be, so you will see the Cherenkov light from all the particles in the shower. So we'll have much more information to deal with. So you can allow a much more precise discrimination. So here it's more poor quality of discrimination because you see only a fraction of particles from the shower. So yeah, and how do you reconstruct the arrival direction in this case? So the arrival direction is reconstructed based on difference in arrival time between different water tanks. So each water tanks, so there is a timestamp when the air shower, so when the Cherenkov flash occurred, and based on difference in arrival times, you can reconstruct the development of air shower, and hence from where the initial particle arrived, so the proton or gamma ray. So in the case of gamma ray, it's very simple because all the let's say all the signal will be concentrated along the direction of the initial gamma ray. So it will be a mean to reconstruct this initial direction, but I have to already say that it is much more, it's much less accurate than for IACT. So the arrival direction is reconstruction is poorer than in the case of Cherenkov telescopes. So let's consider the performance of HAWC. So we're gonna compare its performance to other gamma ray instruments. So what's included here? So this is angular resolution plot, and this is the flux sensitivity. So for angular resolution, you can see, so this is HAWC. So these are currently operating Cherenkov telescope array. So Fermi-LAT and CTA, so the future Cherenkov telescope array that is going to be constructed. So comparison of angular resolution for these different instruments. So you can see HAWC has much poorer angular resolution. So at 10 TeV, for instance, so current Cherenkov telescopes can resolve sources up to 0.05 degrees, right? CTA will be able to do better, so 0.03 maybe, while HAWC is like 5 times worse, so only at 0.15. So doing imaging with HAWC, you will have much less pixels to represent your source, so you'll have much more poorer quality images. So that's a drawback. Then for flux sensitivity, you can see, okay, current Cherenkov telescopes, so at 1 TeV, the lowest flux that they're sensitive to is around 10 to minus 12, 10 to minus 12 erg per centimeter per second. So it's a spectral flux, so E squared dN over dE, which is, okay, if your source is fainter than this flux, then the Cherenkov telescopes will be not able to see it. But this is for 50 hours of exposure. So if in 50 hours observations, your source is fainter, no signal will be detected. CTA is aiming to improve the sensitivity of current Cherenkov telescopes by 1 order of magnitude or even more. So you can see it here. So CTA will see much fainter sources. So, and Fermi-LAT, okay, why do we still need Fermi? Because it has greater sensitivity at low energies. For instance, below 100 GeV, Fermi is much better. So at, for instance, 10 GeV, so Cherenkov telescopes below 100 GeV, there is very poor sensitivity. So that's not their energy range. So Fermi is operating in more or less range from 100 MeV to 1 TeV, maybe. If your source is bright, so yeah, so HAWC is somewhere in between, so below around 10 TeV or maybe 5 TeV. So HAWC will be less sensitive, but not much less sensitive than Cherenkov telescopes. Okay, but another thing is that you need more exposure. So HAWC is operating for many years, and it will be able to reach sensitivity as Cherenkov telescopes, maybe at around 5-10 TeV. Then after 10 TeV, so the HAWC is much more sensitive because it samples particle, so it samples particles from the air showers, and the more, yeah, the more is the energy, the more energy of the primary particle, gamma ray, the more shower particles you have. So HAWC can detect that very reliably, while for Cherenkov telescopes, okay, is not really the case, because the, let's say, the problem with the technique, so above 10 TeV you have very few, uh, let's say the number of gamma rays which are arriving is very low, but HAWC will be much more sensitive because of its wide field of view. So for Cherenkov telescopes, you will be observing the source for, it has much lower duty cycle, so you will be observing source very irregular patterns. So, and HAWC will be observing more or less all the time. So I will explain later. So HAWC is very great to measure particles, so much greater to measure source spectra above 10 TeV than IACTs. So next slide. So why do we need the HAWC instrument at all? Why not to use imaging Cherenkov telescopes all the time paired with Fermi? The thing is that both techniques, so IACT, Cherenkov telescopes, and water Cherenkov technique, they have both their strengths and weaknesses. So let's consider that in detail. So for water Cherenkov technique, what strengths do you have? So you have wide field of view. So you can see many sources at the same time, like Fermilab. That means that you can, yeah, you can collect much more data over many sources at the same time. And for a water Cherenkov technique has also a very major advantage, which is high duty cycle. So you can observe with ground particle arrays like HAWC during the daylight. I mean, it's totally fine for them, because well, for Cherenkov telescopes, you cannot do that, because you need to detect the faint Cherenkov flashes over the night sky background. And during daylight, this is not visible at all. So for HAWC, the daylight is not a hindrance. So you can sample because the tanks are covered, they're metallic tanks anyway, and the metal is not transparent to sunlight, so, or daylight, so you don't care. So there is a total darkness inside the water tank, so you can see your faint flashes very easily. So daylight is not a hindrance. So during bad weather as well, because you don't care. For ICT, so if you have clouds, that means your chunk of light will be attenuated, so you won't see as much photons or don't see them at all. While for HAWC, okay, clouds don't create any hindrance, because the particles are able to traverse the clouds without any attenuation. So, and Cherenkov photon, okay, you don't measure Cherenkov photon, so you don't care. So you can observe also during clouds. Yes, Douglas.
I just got a small question regarding the situation about light. Like I thought, like for the Cherenkov radiation, light will alter the telescope because it's much sensitive to incoming rays. And then I do know that our sun constantly is radiating a lot of energy. So for the language, it's radiating a lot of energy. So I thought, like, if the sun is radiating that much energy, it will harm the telescope, especially for the ones that are more sensitive. So just wanted some clarity about that one. Like for the water Cherenkov one, like that point, can you just clarify that part?
Yeah, so the observation during the daylight. Yeah, another thing I didn't mention, of course, that, well, you don't only want to detect the Cherenkov light or the background light, so which is absolutely impossible when you have daylight, which is many orders of magnitude more bright, but also because the photosensors like GAPDs or the photomultipliers, they're extremely sensitive to low light flux, so you will be destroying your PMTs with daylight or GAPDs. So you cannot use them even during moonlight is tricky. Only GPDs because of adapting voltage, but PMTs will be burning. So yeah, I remember I was doing shifts for a FACT telescope, so it was like many years ago, like 6 years ago or something. So and it was completely remote operation, so I was doing it from Geneva, and the telescope is on Canary Islands. So and I had to check the status, something about the how the telescope looks like, if everything is okay with the. So as I'm not on site, so there is an infrared illumination. So you activate infrared illumination, and then you can see the telescope. But you need the camera to be closed, like the shutter has to close, and I forgot to close the shutter. So although it was like this, the photo sensors are sensitive in the UV, and this is infrared illumination, so it shouldn't be really that great effect. But I received alerts from the software that the currents are too high, so the PMTs were about to burn. So because it was so like so high flux from like flux, although in infrared, which are PMTs are less sensitive to. So yeah, you have to be very careful with the background light, because the sensors, the photo sensors are extremely sensitive. So you can completely destroy them with too bright light. So yeah, during daylight, you don't observe with Cherenkov telescopes, but for water Cherenkov, so you have tight metal, which is opaque to daylight, so it's not really interfering with. And the metal, I mean the strong sunlight. Okay, I think there is some sort of shielding for these water tanks, so that it doesn't depend on weather at all. So raining or sunny or whatever, so it can withstand that, and no issue, no issues. So was it the question or?
Yeah, that was the question.
Yeah. Okay, so let's carry on. So I stopped on the advantages of water Cherenkov. So again, to summarize, so very wide field of view compared to ICTs, which have very narrow field of view, and very high duty cycle. So we can observe every day without any. There is nothing that can interfere with the observations. And the disadvantages, so I already mentioned a couple of them, but let's point it out again. So very poor angular and spectral resolution, because of you cannot really reconstruct the arrival direction well due to particularities of the technique. So, and the much worse spectral resolution, because you cannot also reconstruct well the energy. So you can, based on this pattern, so the reconstruction has a very limited precision, unfortunately. So and background projection is not very optimal as well. So as I already mentioned, so that's because you sample only part of the shower, and that's it. And for ICTs, you see all the information about all particles which is contained in the Cherenkov light, so it's more precise. And energy threshold is very high, so you cannot observe very low energy gamma rays, like a few hundred of GeV is really tricky, because very few particles will be reaching the ground. The statistics will be poor, your reconstruction will be absolutely horrible. So this techniques works the most optimal above few TeV, let's say. So for ICTs, so the advantages is very good angular and spectral resolution. So due to the fact that I already mentioned, so you see the entire shower in Cherenkov light. So you have good handle to reconstruct all the information, the energy and the arrival direction. So lower energy threshold. So because you don't care, so you receive Cherenkov light from the air shower anyway. So because it's always directed towards the ground, so you always see showers even with low energy. And it features also very decent background projection, so it's more precise in the case of IACTs. So, but the disadvantages is there is something interfering with the observations, like daylight. You cannot observe during daylight. You cannot observe during moon generally. You cannot observe if there are clouds. So in the end, you have to have very specific conditions to observe, and you may miss some interesting behavior because of bad weather or anything. And okay, IACTs, they have very narrow field of view, so it can only observe usually one source at once, while water Cherenkov arrays can see many sources as Fermi. And now a bit different, so a similar comparison of these two techniques, but characteristics by characteristics. So let's sort this out. So ICT arrays, so Cherenkov technique versus ground particles arrays like HAWC. So for energy resolution, what do we have for energy resolution? So Cherenkov telescopes, good energy resolution, ground particle arrays, poor energy resolution. And by the way, to construct spectra, so I have read the paper on how, so performance paper of HAWC, I think end of 2015 or early 2016. So they measured the spectrum of a standard source, which is Crab Nebula with known spectrum. And so they had to assume a certain model to reconstruct their spectrum as it was for Fermi. You remember we were doing that with likelihood analysis, but in fact their analysis is much more sensitive to the initial assumption of the spectral shape. So that's kind of not that great. So you have to be careful when it's just information that HAWC spectral power, like their capabilities for spectral measurements, are much more limited than for Cherenkov telescopes. So angular resolution, again, ICT arrays, so very good angular resolution compared to ground particle arrays. So the low energy threshold, so from which energy you can start observing. So Cherenkov telescopes, you can go as low as 100 GeV or 200 GeV. So for ground particle arrays, typically depending on the altitude, depending on the number of those Cherenkov tanks, it will be maybe 1 TeV, maybe 10 TeV, depending. The higher, the more you can reach, the more you can lower your threshold, but generally it's much more high than for ICTs. Then for duty cycle, so what's the percentage of time you're actively observing? So ICT arrays, very, very poor duty cycle, only 5–10% of the entire time is when you can look at your source. For ground particle arrays, it exceeds 90%, so you have excellent duty cycle. So field of view for ICT arrays, very narrow, so one source at a time, while for ground particle arrays, it's 45 degrees, so you can see many sources and measure many sources at once. Background rejection is very good for ICT arrays and quite medium for HAWC and ground particle arrays. Well, ground particle arrays, so figures here are for HAWC specifically, and for ICT arrays, this is one of the major arrays like HAS or Veritas or Magic. So now capabilities about sources. Let's consider so two particular characteristics. So are we able to observe transients well? So what is a transient phenomenon? Is generally something that occurs, well, something that is occurring suddenly by chance, like a flare of AGN. So you have a steady flux, and suddenly at some point, without even a precursor, so the flux is increasing by an order of magnitude over a few hours, for instance, or a few days, and then drops down to a usual level, so more or less the quiescent level. So these are named flares. And so, or another type of transients are gamma ray bursts. So you cannot predict in advance when the source will be undergoing this variability. So you don't know in advance. So you already can see the problem with ICT arrays, that they, due to their narrow field of view, if there, imagine you're observing a source at the moment, and some other source far away from the field of view is doing some interesting behavior. And how do you know about that? So you need a trigger. You need to know that it is flaring, and you need to, when you learn about the fact that something is going on in some position on the sky, you need to repoint your telescope, okay? While for ground particle arrays, due to their due to their wide field of view, they can see very well the more or less, not entire sky, but a large portion of the sky. So they can, these ground particle arrays, they can see that something is happening for a particular source, and they can give, okay, I mentioned that the angular resolution is poor, but still they can give a more or less approximate position on the sky. So some, let's say, circle on the sky from where this originates, and then you can look up what known sources are located in that circle, and you can repoint your IACT to that source if you're interested to study that behavior in more detail. So, but the thing is that the transients, which you can only observe, are at high energies due to higher threshold. So if something is flaring, for instance, at very low energy, then your ground particle array just won't see that. So another sort of triggers which are issued are not only by ground particle arrays, but of course by Fermi, because it also has a very wide field of view. So it can see the large portion of the sky and see flaring phenomena or gamma ray bursts and issue alerts. So, and then the telescopes like HAWC or others, they can point at the source and measure these sources during interesting behaviors with good energy resolution and good angular resolution and with good background projection. So you see the point. So ground particle arrays and Fermi-LAT, so it's a separate case. So Fermi-LAT can also issue alerts, but ground particle arrays are excellent for spotting, quickly spotting some interesting behavior, variability at high energies, and letting know to ICT arrays so that they can observe it with excellent quality. So for full sky surveys, so monitoring the sky in TV gamma rays, so ICT arrays, obviously they're not suitable for this task. So they have very narrow field of view, right? While ground particle arrays, they can sample, so they can observe a wide portion of the sky for many years combined with high duty cycle. So every day you have information from a large portion of the sky. So you can have full sky surveys very efficiently with ground particle arrays. So it allows you to find new sources, for instance, or well, things like that. So in conclusion, so IACTs, Cherenkov telescopes, they're good for studying precisely and accurately the individual sources. So, and they have very low energy threshold, so you can observe up to a few hundred of GeV. While water Cherenkov like HAWC is best suited for sky monitoring, so finding quickly transient phenomena, making full sky surveys, and they're much more sensitive at higher energies. So at the end, HAWC complements very well the Imaging Atmospheric Cherenkov Telescopes. So if you combine the weaknesses, so if you combine the strength of one technique with the weaknesses of another, so you will be closing these gaps more or less. So these techniques complement each other very well. And a few lectures ago, yeah, someone was asking me why we're building CTA and not bigger Fermi-LAT. So exactly for this purpose, because CTA will be excellent for good energy. So for individual sources, it will achieve much better performance. And HAWC will be complementing CTA and providing valuable input, yeah, about transients and making full sky surveys. So yeah, So one technique perfectly complements another one. And now, yeah, the final slide for today. So now about the science goals of HAWC, what we can do with HAWC, what we are doing with HAWC. Well, I mean, I'm not a part of HAWC collaboration, but yeah, I'm talking about, yeah, scientists who are analyzing HAWC data, what's their goals. So okay, of course, studying extreme acceleration at TV energy scale. So different sources in the galactic accelerators. So why galactic? Why not? Why we can't observe extragalactic behavior? Yeah, this is because HAWC is much more sensitive in the range from 10 TeV to 100 TeV, and gamma rays with this energy. Have you heard about the gamma ray horizon or opacity of the universe to gamma rays? So if you haven't heard, so a quick introduction. So in fact, the whole universe is permeated with extragalactic background light. So it's a infrared and optical light, which is the, let's say, so it's all the light of all the stars and galaxies emitted throughout the entire history of the universe plus redshifted. So, and it's, yeah, also another component. So infrared component is the same light, but reprocessed by dust. So when optical light interacts with dust, so it heats the dust and the dust re-emits in infrared. So these two components, so the gamma rays, they can interact with this low energy light background. So extragalactic background light is abbreviated usually as EBL. So when a high energy gamma ray is colliding with an EBL photon, so it produces electron-positron pair and the photon is lost. So due to this ubiquitous radiation field, the EBL, you have attenuation of gamma rays from distant sources. So this attenuation, so the density of this emission, depending on the wavelength and the interaction cross-sections are such that this process starts to be important above, let's say, 100 GeV or a few hundred GeV. You have more and more significant attenuation with energy, and it reaches the peak at a few PeV, so 1000 TeV, and then above 100 PeV, you go down, so you have less opacity. But yeah, at 100 GeV, you have, let's say, the gamma ray will be propagating for around 500 megaparsecs until it will be attenuated. So, and at around 100 TeV, so 3 orders of magnitude higher, so at 100 TeV photon, a gamma ray will be propagating only 8 kiloparsecs or 10 kiloparsecs until it will be attenuated. So you see, so the net result, so the main idea is that you cannot see gamma ray sources which are in the range of 100 TeV. You're not able to see sources which are more distant than a few tenths of kiloparsecs. That means that you cannot see anything extragalactic. You can only see sources which are within our galaxy in this energy range. So that's why galactic accelerators. So HAWC is detecting mainly, so in the range of 100 TeV, is detecting only TeV emission from the galactic accelerators. So it can allow to, so when you learn for instance, you learn the spectra of the galactic sources, so the distribution of the gamma ray flux depending on energy. So this can allow you to have a reasonable idea on what's going on in the source, in particular how acceleration processes are working. So because the gamma ray spectrum can indicate you the spectrum of particles in the source which were emitting these gamma rays, and hence you can reconstruct what was the acceleration process. And the acceleration processes at these energy scale, like 100 TeV, are not that well known. So there are different scenarios, acceleration scenarios, which are supposed So shock acceleration or diffuse or magnetic reconnection or more exotic scenarios. So it all boils down to study of how particles are interacting at this energy scale, because we only have Large Hadron Collider, the most powerful accelerator, human-made, which is only operational up to 14 TeV in the center frame. So, and here you are going 2 orders of magnitude higher. Okay, so we are not sure what are exactly the behavior of particles at these energies. So HAWC is very valuable in this regard, because IACTs, Cherenkov telescopes, they cannot really reach well 100 TeV scale. So a few tens of TeV with long observations, yeah. But HAWC can really go much further in energy, so we can study more violent phenomena with HAWC. Next, so observation of extended sources. So many sources in the galaxy, for instance, Large Magellanic Cloud or Crab Nebula, they are extended. So it means that the size of the source is longer, or let's say larger than the PSF, the point response of the telescope. So obviously with Cherenkov telescopes like HAWC or MAGIC, you cannot observe very extended sources well, because it might be much more extended than your field of view. So this is where HAWC is helping you out. So due to due to wide field of view, it can see the entire source at once. So it can allow to better map these extended sources. Next is to study the emission from the galactic plane. So I was showing a couple of lectures ago, I was showing the gamma ray map of the entire sky, and the galactic plane was shining in gamma rays because of the interaction of cosmic rays with the interstellar gas. So cosmic rays, which are produced inside the galaxy, but also outside the galaxy. They're striking the protons of the neutral hydrogen mostly, and due to this interaction, so neutral pions are created, and they decay into 2 gamma rays, and you have gamma rays coming from the galactic plane. So this is where the most of the neutral hydrogen is concentrated. So the galaxy is very inhomogeneous. So, and the cosmic rays, despite the homogeneity of the extragalactic cosmic rays, so inside the galaxy is not really the case, because you have sources which are not distributed homogeneously. So you have anyway an isotropic creation of this emission, the gamma ray emission inside the galaxy. And so we need to study that better, and we can rely on Fermi at lower energies, around 10 GeV, but we need advantage of HAWC, of wide field of view and access to higher energies to map the diffuse emission and characterize this process of interaction better at higher energies. Then next scientific goal is, I was already talking about, so this is issuing alerts for transient phenomena. So for instance, AGN flares or other transient phenomena in gamma rays. So HAWC, due to its wide field of view, it can spot interesting behavior in TeV energy range, and all scientists on duty, they can report it to other collaborations like HAWC, Veritas, and so they can point their instruments to these. They can point these instruments to these sources. I can even show you something now, because currently from 12 May to 25th May, I'm on duty for these transients. So I'm monitoring different alerts and different plots, so to spot interesting behavior. And so it's for HAWC, so to point HAWC to sources which show interesting behavior. So a typical alert from HAWC looks like this. So sorry, from HAWC. So I can find in my email, yeah, for instance. So this was issued on May 18, a few days ago, from HAWC monitor. So there was previous email, yeah. So new HAWC alert from HAWC online server sent. So source category, source association. So this is the name of the source. 3C66A. So this is an active galactic nucleus. So the coordinates Ra and DEC. So redshift not known. Okay, and trigger time. So when the flare was triggered, and okay, false alarm rate is something specific. So yeah, so I received this email and I reported it into HAWC collaboration, and they were first you need to see if the source is visible at all for HAWC, because it's in different. So HAWC is in Mexico, HAWC is in Namibia. So you need to, well, you might not be able to see. So you check if you can see that source, if there is indeed something interesting, or yeah, if it's worth at all observing with HAWC. So, and yeah, then the decision is taken by the monitoring group whether we point HAWC telescope to that source or not. So yeah, so this is one example. So where HAWC is really useful. And yeah, and finally, you can also use HAWC to study gamma ray bursts. So gamma ray bursts are the most energetic phenomena in the universe, in fact, but in electromagnetic form of energy. So okay, there are three levels. So quasars are the most bright sources in the universe with persistent flux, let's say, well, constantly shining, you know, non-transient phenomena. So the most energetic phenomenon in electromagnetic form of energy is a transient phenomenon, gamma ray bursts. And the most energetic in general phenomenon, the most energetic phenomenon in general is the black hole mergers. But here the energy is emitted not in the form of electromagnetic waves, but in form of gravitational waves, which is different. So yeah, this is just sort of comparison. So gamma ray bursts, yeah, the most energetic phenomena in electromagnetic waves. So the yeah, there are very different. There are two different classes of gamma ray bursts. So short gamma ray bursts and long gamma ray bursts. Yes, Douglas.
Just a quick question. You mentioned something quite interesting about the measure of black holes. Can you just enlighten that situation again? I just, like, you went by quickly and I was like, what? Like, so can you just repeat that point again?
So you mean about the scale of energy, right? Comparison, the most
energetic. Yes, you mean
phenomenon.
Something about black hole. I don't know what you said. You just went by, quickly went by a black hole. I was like, what? You mean?
Yes. So yeah, I was saying that the most energetic phenomena in the universe in general by the amount of energy released are black hole mergers. So maybe you heard 2016 February, probably there was a well, confirmation that the gravitational waves exist, that the Einstein theory of relativity is correct, things like that. So it was detected by LIGO, right? So the ground-based gravitational wave detector, and so yeah, so it's a specific type of source. So binary, so a black hole mergers. So these are two black holes which are revolving around one another, and the pair of black holes, so due to they curve the space-time, so these pair of black holes, they emit gravitational waves, so they lose energy, and so they kind of fall one on each other. And so once they get so close that they actually merge, and like a burst occurs, so gigantic amounts of energy are released. So but they're released mostly not in the form of electromagnetic radiation, because there is nothing, I mean, there is no channel, I mean, there is no way they can interact electromagnetically, but they only interact gravitationally. So the energy is released, 99% of energy is released in the form of gravitational waves. So gravitational waves is when, so imagine it's like a wave on the space-time, like sort of, yeah, sort of, imagine you have a blanket and you start shaking it, so you'll have a wave propagating over the surface of the blanket. So the same is, instead of blanket, you have space-time. So this is kind of this wiggling, propagating over the space-time. So yeah, most of this energy, so in terms of energy released, they're brighter than quasars, they're brighter than gamma ray bursts, but it's not electromagnetic waves, so it's not radio waves or gamma rays or whatever. These is different, these are gravitational waves. So I'm just comparing different scales of energy. So gamma ray bursts are the most energetic phenomena that are outputting their energy in the form of electromagnetic waves. So visible, yeah, radio waves, X-rays, visible light, all, so electromagnetic spectrum. So I hope this responds the question. And so yeah, gamma ray bursts, there are two types. So short gamma ray bursts, so this is when not black holes, but two neutron stars are merging together. So they feature also a very strong gravitational field. So two neutron stars which are merging. So you have, okay, you have also gravitational waves, but as contrary to black holes don't allow the light to escape. So we don't have release of electromagnetic energy. The neutron stars, they allow the light to escape. They only redshifted, but they allow light to escape. So we'll have release of electromagnetic energy, a very significant one. And long, or let's say, yeah, short gamma ray bursts, and I think the second class is named long gamma ray bursts. So, or extend, I think long gamma ray bursts. So this is a different type of source. So this is end state of evolution of very massive stars, which have their mass above, I think more than 50 or 70 mass of sun, solar masses. So the most massive stars, they explode in the form of gamma ray burst. So it's completely different. So low mass stars, so below 8 solar masses, it will be just a white dwarf. Then between 8 and 20, 30 solar masses, it will be neutron star. About 30 solar masses stars will be ending as black holes. And so for most massive stars, it's the most violent phenomena. So it will be gamma ray bursts. So these are, it's a very complicated process and not well studied. I'm not going to go into details now, but yeah, so either black gamma ray bursts is either two neutron stars which are merging together and releasing a lot of energy, or just very massive stars exploding at the end of their life. So these phenomena are happening, in fact, every day. Every day there is one or several gamma ray bursts observed, because the universe is so large. So you cannot really spot gamma ray bursts easily with IACT because you have a narrow field of view, while HAWC or Fermi, they have very wide field of view. So HAWC is able to spot gamma ray bursts which are proceeding at very high energies in the 10 TeV range. And again, issue alerts to other instruments which can be observed with HAWC, for instance. So, but also HAWC is very useful to in fact, as it has wide field of view and large duty cycle. So it's very useful to see the statistics of gamma ray bursts. So it's due to its virtues. So HAWC can observe many gamma ray bursts over years, and so over 5 years already, or 6 years already, it accumulated a significant amount of data, which allows statistical studies of gamma ray bursts, like concentration, if they're homogeneously distributed over the sky, or there is some clusters of gamma ray bursts from where they're more. And you can spot, for instance, for long gamma ray bursts, you can know, okay, maybe that region in the sky, there is a lot of, long, high mass stars, etc. So you can study statistical properties. also, I didn't put it here in the slides, but the last comment about scientific goals is the multi-messenger studies. So neutrino. So if a neutrino is detected from some source, we are curious about if it's also emitting, if the source is also emitting gamma rays. Like this, we can better understand the source, and so HAWC is is able to respond quickly. So HAWC, which is observing all the time, so you can see in the data whether from that region on the sky and that specific time and position on the sky whether there was gamma ray activity. But yeah, the thing is that it's only at at very high energies, above 10 TeV usually, but that's already useful information. So combined with Fermi-LAT, so one can do really multi-messenger studies and investigate whether, for instance, neutrino flashes were accompanied by gamma ray flashes. So that are the main scientific goals by HAWC. And so yeah, that's all for today for my lecture. Yeah, thanks everyone for your attention, and any questions, yeah, you can ask. Yes, Douglas.
Just one last quick question I forgot to ask Natalia before we ended the class. I don't know if you can. Like, it's just about the detection wherever we're using Cherenkov radiation. I just wanted to know, like, are we only detecting burst, or are we detecting something in a more constant way? Like, for example, if we were to, let's say, look at a source for active galaxy to say, like, will you only be detecting burst in the Cherenkov radiation, or will you only detecting like constant thing, which is like there? Like, I don't know if you understand the question. Like,
Yeah.
let me just.
So you mean the source behavior? If we are only
Yes.
detecting like flashes when there is increase of
Yes.
gamma ray flux? Not at
Yes.
all, because yeah, the sensitivity plot shows you that, so HAWC or Cherenkov telescopes, so you can measure any flux which is higher than for a given energy, 1 or 10 TeV, let's say 10 TeV, you can measure flux only which is higher than 10 to minus 12 from a given source. So if your source is bright enough, if it's 10 to minus 11, for instance, which are few blazars, Crab Nebula, so you can observe it if you point your telescope there and there is nothing happening, it's just steady source, then you will be able to see flux. So you will be able to see steady flux, and then if there are some flashes, for instance, from bursts or flares from blazars, which are active galactic nuclei with jet pointing towards you, so you will be able to see increase of flux. So yeah, you can observe during quiescence. Is it what you wanted to know, or? Yeah, maybe I can show you I'm thinking how to. Yeah, maybe I can show you light curves. You know the evolution of flux versus time. So I'm thinking what is the best. Maybe from my PhD thesis, so I was modeling multi-wavelength data. So it was Fermi and not only gamma rays, but from optical to very high energy. So something like this. Oh, yeah, I have to. So yeah, so okay. So for instance, I was studying a flare of an active galactic nucleus, blazar Markarian 421. So you can see, for instance, so this is Fermi data. And so you have low flux at the beginning, there was nothing happening. And then there was a flare So this is a model and these are data. So there was a flash and then it returned back to usual values. And then for Cherenkov telescopes, so I had a few of them taking data available. So for instance, Hagar is an Indian, okay, I think Hagar, by the way, is not a Cherenkov telescope, it's a ground array. This is one of, but it's not, it's smaller than HAWC. So high altitude ground array. So this is data of Hagar measuring. So you can see it doesn't work well. So it was only measuring more or less during flare because it has not that great sensitivity at this energy. So it was only recording flash. There was no data before, but also how do you know? Because this is wide field of view. So technically it was no problem that it could see here. So you don't have data because it was not sensitive enough to lower flux. Contrary, so this is Veritas data, and Tactic is another small Indian Cherenkov telescopes. So this is Veritas. This is, so they were measuring. So why Veritas has only part of the data set? Why not as complete as here? Because Veritas has narrow field of view, right? So it wasn't pointed at the source during the days, and so it was. So an alert was issued by Fermi, I think. And so once this flux started to increase, so they triggered Veritas observations and they only took this part. And then there was more interesting source. So they were, you see, this is problem with IACT data that you only have samples. So only the data, like large observational gaps. So with altitude, like high altitude ground arrays, okay, you're not sensitive enough in some cases. So Indian telescope occasionally, somehow it was observing, so Cherenkov telescope. So how is it actually, acronym stands for, okay, you know, I don't remember already how is Tactic decoded in something, Cherenkov telescope with imaging camera, but TA, I don't remember. I'm sorry, but it's a small telescope, Cherenkov telescope operational in India. And so it was occasionally monitoring the source during that period. So you see it was measuring flux from the source in quiescence. So there was steady flux, so it was observing, and then there was a flash. So, and then some other interesting source was on the way. So yeah, there is no problem to observe non-transient phenomena. So the only thing is that these observations are typically less interesting. So you want to study some interesting behavior like flares. That's why. And so for the spectral data, so yeah, this is the evolution of the spectrum during this flare I was studying. So okay, maybe I will show you, you know, a low state measurement. So this source, Markarian 41, it's an active galactic nucleus. So in 2009, the source was showing very steady quiescent flux. And we want to know as well what's happening in the source, what processes during the quiescence. Oh yeah, yeah, this is my PhD thesis, it's very detailed, so I will find it now. The measurement during the low state. So I will convince you that, yeah. So this is the observation of the Markarian 41 blazer during no flares. So when there was nothing particularly happening, there was steady flux, and the instrument, it's a bright source, so the instrument is quite sensitive to it. So it's a multi-wavelength snapshot, so SED. So you see, so somewhere, so this is Fermi data up to here. Then starting from here, this is data of Cherenkov telescopes. Let me see another plot where it's broken down. Yep. So Fermi data, then this is Imaging Cherenkov telescope. So, and these are instruments in other wave bands. So in fact, so it was a specific campaign to observe the source during when there was no flares. to understand what the process is in this source during when there are no flares. And the goal of my work, in fact, was to connect that measurement with measurement of flares, so to understand how exactly which perturbations are happening in the source when we proceed from low state configuration to flaring. What's actually triggering those flares? So usually people are modeling flares, I don't know, just some injection flash. So I went one step further. I was representing them as perturbations. So I first found out what's the state of the source in the low state with no flares, and what's responsible for perturbing that state, and how do we can generate flares. So for that you need measurements in the low state and in the high state, and you can connect them. So yeah, you can see sometimes instruments are interested in measuring when there is no activity happening, and for these specific reasons, to be able to connect low to and high states. And yeah, so if your instrument, if your Cherenkov telescope is sensitive enough to these fluxes in the low state, then no problem, you can indeed measure. You can indeed measure these fluxes. Any other questions? I don't know. Okay, doesn't seem like the case, so I can stop sharing the screen. Yeah, or I have to first stop recording. I don't know. It doesn't work. Okay, stop share. Good. And I can stop record. Oh, there was something in the chat. Please share the book. Okay. It was okay. So great. So we are good for today.